Assalamu alaikum everyone. Welcome to the course of Embedded System. Today it will be our 7th lecture and we will continue chapter number 2 of Custom Single Purpose Processor. Previously in this chapter we discussed about transistor, the CMOS technology used for the implementation of NMOS, PMOS and gates built using these transistors. We discussed about the combinational logic. We discussed about several basic combinational logic components. For example, we talked about mux, its inputs, its outputs. We talked about decoder, its inputs and outputs. We talked about another combinational logic component, adder and comparator. Along with this, we also discussed arithmetic logic unit. These components were introduced to save the design from getting complex, because if you are going to use gates at every point, your design will get complex. So that's why we introduce components like this: multiplexer, decoders, adder, comparator and arithmetic logic units. Later we talked about sequential logic, in which we discussed flip-flops, because flip-flop is the basic ingredient of sequential logic circuits. In this I told you about the sequential logic made from D flip-flop, SR flip-flop and JK flip-flop. We discussed the difference between combinational logic and sequential logic. As you know that combinational logic, the output depends only on the present input, whereas in sequential logic, the output depends upon the present and as well as past output. We also discussed the role of clock signal and the occurrence of event during the rising and the falling edge of the clock pulse. Along with this, we discussed the register transfer level components. For example, if you remember, we talked about n-bit register, we talked about n-bit shift register, we talked about n-bit counter. And then we designed a simple system in which we slow down the clock pulses, and then we converted that system from sequential logic to combinational logic. Finally, we discussed a custom single purpose processor to compute the GCD of two numbers. I told you about the black box, in which you can only see the inputs and outputs, and the black box is your GCD calculator. We discussed the algorithm, that is the program of the GCD, and then from that algorithm we implemented the state diagram. In today's lecture we will talk about the template for creating the state diagram. So we will talk about the templates for creating the state diagram, and we will discuss the steps. There are 4 steps for constructing the data path of the finite state machine controller. So, and after that, once we are done, we will look at the optimization of our finite state machine. Okay, so let's begin with our first slide. So in this slide you can see that we have 3 things that you will always encounter in a program, in an algorithm. That is assignment statement, loop statement and branch statement. So whenever you have a program, so from program, when you need to generate a state diagram, we are going to use this template. So for any assignment statement, for example here A is equal to B. For this, what we need to do, we need to define a box like this where A is equal to B is an assignment, followed by next statement. Likewise for loop, for example we have a while loop, so while loop, its condition, its body and then next statement. So you need to be careful about its template. So template is like that. C represent the condition. If condition is not true, it will go to next statement. Okay. However, if the condition is true, that is cont. not this one. Okay, so if the condition is true, it will come into the body, and there must be some jump because it will need to go back as long as the condition is correct. I hope that you got this point. Now the final template is for branch statement. So we have couple of if, one if statement followed by else if statement. So we can have any of them true. We can have C1 true, we can have C2 true, or else is true, followed by next statement. So this is the condition C. If C1 is true, this will execute. If C2 is true, this will execute. If none of them is true, neither C1 nor C2, this will execute. And then we will combine all these in order to go to next statement. So this is the template that we need to follow for branch. You can compare this template with the state diagram of GCD, and this is the template we need to follow for loop, and this is the template we need to follow for assignment. Let's move to next slide. So the next is how to create a data path. How to create a data path using this state machine. Okay, so this is state machine with data. How we can generate this data path? So there are 4 steps that you need to follow. Number 1 is, first we create register for any declared variable. For example, in this example the variable are x and y. This x and y, these are our register. We create output as an implicit variable so that we execute a register D and connect it to the output. So this is our output register. So we have x, y as our input register, and we have D our output register. So this is number 1 step, to create a register for any declared variable. Okay, now second point is we create a functional unit for each arithmetic operation. In this example there are 2 subtractions. So this subtraction is our functional unit, this subtraction is our functional unit, this less than is our functional unit, and this not equal to is our functional unit. So second step for creating the data path. Now third is to connect the ports, registers and functional unit based on read and writes. So on the basis of read and write, we connect the ports, register and functional unit. Use multiplexer for multiple sources. So you can see that we have connected the register and functional units. Here, let me choose this thread. So this is our register. This is connected to this functional unit, this functional unit, this functional unit and this functional unit. Okay, similarly this register is connected to this functional unit, this functional unit, this functional unit and this functional unit. Okay, and these are our ports. We will talk about these ports later on. Like these are our output port, x not equal to y, x less than y, d load, d out, x select, y select. So these are our output ports. Now let me rub these out. Okay, so now moving on to our next point, that is our last point, create unique identifier. Unique identifier means for each data path component there must be control input and output. Okay, so for this we have, for example in this we have x select is our control input, y select is our control input, that will come from controller. Okay, and then these are our control outputs. This x not equal to y, x less than y, d underscore out, these are our control outputs. Okay, So that was about like creating the data path. Now let's move on to our next slide. So now what we need to do, we need to create the finite state machine of controller. Now you can let me highlight this one is finite state machine with data, whereas this controller is finite state machine, there is no data, and this is the data path. So same structure as FSMD, you can see the structure of this is same as of this one. Okay, so same structure, the structure is same. Okay, replace the complex action with data path configuration. So let me point out what we have changed so far. Number one change is this external go signal. So this process will start as long as go underscore I is high, mean 1, and then we have an infinite loop. If y is 1, we will go further down, and if go underscore I is high, it means we will go to this x underscore select is equal to 0 or x underscore load. So now if you compare this, here we are doing assignment x is equal to x underscore I. It means we are assigning external input x underscore I to x. Now when we convert our FSMD from to FSM, you can see here this is multiplexer, this is multiplexer, because we have two inputs, number one x of I for this one, and then this second input that will be the state 8 output after the subtraction, and here we have y of I for this multiplexer, and then the output of 7 state. Okay, so now initially what we need to do, initially we need to select x select must be 0, so that we can load whatever x of I is coming. In next state we will load whatever external input y of I is coming. Then now at 5 you can see these are complex action, not x not is equal to y. We have simply replaced this with not x not equal to y. So as long as this statement is true, like x not equal to y is false, we will go to this. It means it will go to this point. It means our code is stopped. Okay, so as long as x is not equal to y, what we are going to do, we will compare these two. Okay, and this is same template. After the if statement we have space, then we are splitting these two, 7 and 8. Now in 7 and 8 we are going to this, you can see here this is 7. In 7 what we are doing, if x is less than y, we are going to update y, so this y is updating. Okay, so for this we need y select to be 1, whereas if x is not less than y, so what we are going to do, we are going to update x, and this is going here. Okay, clear? So in both cases when we are going to update x and y, we need x select to be 1, and x load obviously because we want to load these values to register. These are registered, sorry I forgot, these red one are registers. Okay, so there are two clocks for these, and this is your register. So once we are done from this 7 and 8, where we will come, we need to combine. Okay, we need to combine. So this is 6 jump. Here we were separating, so here we have to combine, and now this 5 minus 6 is in relation with this 5. Okay, so you can understand this from the template which I have already told you. The only point that you need to understand here is this is finite state with data, whereas this is controller in which we are using only finite state machine. So these are states 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and then we are using complex action and condition with data path configuration. So this is data path configuration, not x not equal to y, not go, s select. These are data path configuration. This you can see this. These are data path configurations. Okay. So I hope that this slide is also clear. If you have any question, you can ask me later. Okay, let's move on to next slide. So in this slide, what we are trying to do, we are splitting the controller and data path. So this one is controller. It's a minimized version of this controller. Okay, and this is our data path. So in this controller, you can see because Q3, Q2, Q1, Q0, these are your present states, and I3, I2, I1, I0 or I0 is your next states. Okay, and these X select, Y select, X load, Y load, these are your outputs to the data path, as you can see here. Okay, whereas X not equal to Y, X less than Y, these are controller inputs from data path. Okay, and then this is the output of the controller D underscore load. Okay, as sorry, not this one, in fact this one. Okay, so the only thing that we are left with is combinational logic. So we have used the same technique as I defined earlier in the case of clock slowing down. So we have used the same technique to complete the controller design by implementing the finite state machine using sequential logic technique. Now this figure shows controller implementation model, and what's inside this, let's check this out in next slide. So only thing that we are left with is combinational logic. I hope that rest of the things are clear. This is the control, this is the signal, that is the input to the controller. Go underscore I will be 1, only then it will start. So I hope that this is the inner portion, okay, inner portion, and then these two are connected. This is data path and this is your finite state machine. Let's move on to next slide, in which we will see the combinational logic, how we have defined the combinational logic. So as you can see that there are 4 bits, 000, 0001 up to 1100. So we need 4 bits for present and 4 bits for next states. Let's move on to next slide. So if you see in this figure, a state table for the controller is shown. Okay, so state table for controller is shown. However, this table is reduced by using static for some inputs, and you can see that we have 7 inputs. These are 7 inputs. Let me point out for you. 1, 2, 3, 4, 5, 6, 7. So 7 outputs, total combination will be 128. So we have reduced it down to only a few, and few are mentioned here. Okay, we reduce rows in state table of the figure by using statics. So we have used statics for some input combination, but we can still see that optimizing the design using the hand technique could be quite difficult. For this reason, CAD tools, computer aided design tools that automate both the combinational and sequential logic design can be very helpful. And of course, we will introduce some CAD tools in the last chapter. CAD tools that automatically generate digital gates from sequential program, finite state machine with data, finite state machines, or logic equation are known as synthesis tools. So we can use synthesis tool to reduce this big table of states. So now you can check this out I'm just going to explain one of the line here. Let's look at, sorry, let me clear this out. So let's look at this first line. Okay, so Q3 is 0, Q2 is 0, Q1 is 0, and Q0 is 0. So you are at state 1. Okay, so x not equal to y is not defined, x less than y is not defined, go underscore I is not defined, so nothing is defined. So what is going to happen? We're going to move to next state 0 0 0 1. So you can check I0 is 1, I1 is 0, I2 is 0, I3 is 0, and X select is don't care, Y select is don't care, because at this particular state we do not need X select. We need X select only when we reach at the assignment. Okay. Also we do not need loading. So loading is particularly 0 here, and the D underscore LD is your output. Okay. So let me check where we will load. So if you check this line, here we are loading X. Here we are loading X, and of course you can compare this state table with your state flow diagram, so it will make you further understand like what is happening here. So we are at state 0 0 1 1, and x not equal to y is not defined, x less than y is not defined, go underscore I is not defined. But what is happening? We are moving to 0 1 0 0. You can check that in your state table. So X select is 0, Y select is, we're not, it don't care. However, X load is 1, it means that we will need to load X. Okay, so we are loading X, and Y load is 0, so it means that we are not loading Y. And similarly, output is 0. Clear? So you can go through the state table one by one. You need to see the state diagram along with this state table. So I hope the things will be clear once you go through this complete table. Okay, so let's move on to our next slide. So we have finally completed our GCD custom single purpose processor design. We finished the data path. We have state table for next state and control. So we have this thing done, we have this thing done. I told you about the functional units, that was comparator, less than, greater than, subtractor. I told you about the registers. So our data path is done. Our only thing that is left, all that is left is combinational logic, and you can find this, you can compute this combinational logic from your present and next states. So you just need to find out the equation for I0, I1, I2, I3, and similarly for X select, Y select, and so on. Okay. However, this is not an optimized design, but we see the basic steps, like what are the basic steps to create a custom single purpose processor. You need to understand the template for while, for if, and for assignment. You need to understand what are the components, what are the 4 steps for designing the data path, and how we can create the controller. So if you go to previous slide, you will see the important ingredients of a controller are combinational logic, state register. So combinational logic, where the combination, here you will have combination logic, in control logic here in yellow portion. Okay, so that's about it. Let's move on to our next slide. So in this slide we're going to look at the register transfer level design of custom single purpose processor. So we often start with state machine rather than algorithm. So we do not write program or algorithm. Most of the time we start with the state machine, and cycle timing is central to functionality. This is because we take care of cycle by cycle timing in finite state machine, whereas in programming languages we do not support cycle by cycle description. Okay, so here we have an example with problem description is that we have a bus bridge that converts 4 bits bus to 8-bit bus. So we start with FSMD, also known as register transfer level, and then we complete this exercise. So let me explain you the problem statement in more detail. We want one device, the sender, to send an 8-bit number to another device, the receiver. The problem is that while the receiver can receive all 8-bit at once, so this receiver can receive all the 8-bit at once, and this sender can send only 4 bits. So we need a bridge. Okay, so we need a bridge that does that. So first it sends, so the sender sends 4 bit at first time. First it sends the lower 4 bits, then the higher 4 bits. So we need to design a bridge that will enable the two devices to communicate. So we need to design this bridge. Okay, so how we can do that? Different designer might attack this problem at different levels of abstraction. One designer might start thinking in terms of registers, multiplexer, and flip-flops. Another might try to describe the bridge as a sequential program, but perhaps the most natural level is to describe the bridge as a finite state machine with data. Okay, so this is the finite state machine with data. Let me explain it to you. We begin by creating wait first 4. So this is our first state, wait first 4. We are going to wait for first 4 lower bits. As long as ready in is equal to 0, we are at waiting state. When ready in becomes 1, it means this input signal become 1, and what we are going to do, we receive first 4 bit start and we are going to put them in data low. Whatever at the input is coming, we will put in data low, and then we will move on to next state, that is receive first 4 and now here you can see that ready in is still 1. As long as ready in is 1, we will wait for pulse on ready in to become 0, and then now you can see that the ready in becomes 0, so we wait for second 4, and we are going to wait as long as ready in 0. Once ready in become 1, we will receive the last 4 bits, that is higher bits, and data high is equal to data in, and then receive second 4, and we will wait till the end of the 4 bits, and as long as ready in is 1, we will remain in this state like the way we were in this state. Okay, now ready in 0, what we need to do, we do not need to wait for ready in to become 1. Rather, what we will do, we will combine these 2 bits, data high and data low. Okay, we will combine, let me highlight this, data high and data low, and ready out will become 1. Okay, so now we will send it. Now as long as ready out is equal to 1, we will send it, and we will end this when ready out become 0. So we have these inputs, ready in is your input, okay, data in is your input. So these are our inputs. Let me highlight here, ready in, data in, and these are ready out your output, data out is your output. So output ready out and data out. And variables, what variables we are using, data low and data high are our variable. So this is how we can make finite state machine with data rather than making a program or algorithm. We start with finite state machine, and what we have used here, we have used registers here. Okay, register transfer level. So we are sending first 4 bits, then we are waiting the pulse to get change. So that's why we have received first 4 end. Then we wait for next 4 bits. We have received second 4 start, and then we wait for the pulse to get 0. Then we move to next state. Okay. Now in next slide we will see how we can convert this finite state machine with data to finite state machine with data path. So we will have a finite state machine controller and separate data path. Let's move to next slide. Before I move to next slide, let me clear this out. Okay. So now in this slide we will convert our finite state machine with data in 2 parts. There is controller and data path. In data path we do not require any functional units because we are not performing any sort of mathematical operation. So we will have only registers here, data out, data low, data high, and this will be combined. So while making this data path, we need to keep track of those 4 steps that I've told you. Like we need to use register for variables, we need to assign unique identifiers, we need to define function units, and then there was one thing more, that was, let me tell you, yes. So first was to create register for any declared variable, the second was we create function units. So we create register for declared variables. So declared variables were, what were your declared variables? Your declared variables were data high, data low, data out. So these are your declared variables. Okay, and this is also your declared variable. So data in 4 is going in both data high and data low. Okay. Second, we create a function unit for each arithmetic operation. So there is no function unit, we just have register here, data high, data low, and data out. Third, we connect the port, register, and function unit. So we are connecting the ports. So these are unique identifiers. Look at this, data high, this is signal for loading, data high. Okay, this is signal for data out load, this is signal for data low load, and this is for data out. So this is our output, this is our input data in, this is our clock, this is ready in signal, this is ready out signal, this is controller, and this is almost similar to what we have in FSMD. There is no change in this except we just use some, like rather than data in we are using data low, load is equal to 1. Okay, so it means that the bit is high. Here data load is equal to 1. So it's just that we have changed those complex operation to simple ones here. Okay, so you can compare this finite state machine with the finite state machine of GCD, and you just need to take care of those 4 points. So inputs here are ready in, let me again tell you, and your data in is your input. Outputs are ready out and data out, whereas variables are data low and data high. So we need 3 registers here, data high, data low, data out. And I told you we do not need any function unit because we are not performing any sort of multiplication. Okay, so I hope that this is clear. So now let's move on to next slide. So optimizing single purpose processor. You may have noticed that in our previous GCD example, we ignored several opportunities to simplify the resulting design. For example, the finite state machine had several states that obviously do nothing and could have been removed. So if you see the template, there were some empty blocks in the template that were doing nothing. Likewise, the data path has two adders, whereas one would have been sufficient. So we have like two subtractor for x minus y and y minus x. So one would be sufficient. We intentionally did not perform such optimization so as not to detract from the basic idea that programs can be converted to custom single purpose processor through a series of straightforward steps. However, we rarely design such processor. We will usually want to optimize them whenever possible. So optimization is the task of making design metric values the best possible. So we have following opportunities for optimization. Either we can reduce our program length, like we can optimize our program, we can optimize our finite state machine with data, we can optimize. Now finite state machine, optimizing finite state machine with data means like reducing your states, okay, reducing your comparison, reducing your loops, like that. And then and we can reduce our data path like combining function unit. Rather than using two adder, two subtractor, two multiplier, we can use simple one subtractor and we can perform both of the operation from there. And then finally optimizing your finite state machine. So we can do that. So let's start with original program and see what other program we can write for calculating the GCD. So the first step was to optimize the original program. We can analyze our program attributes and look for areas of possible improvement. We can reduce the number of computation, we can reduce the size of the variable, we can reduce time and space complexity, we can reduce operation use like multiplication and division because these operations are very expensive. Okay, we can try to develop alternative algorithms that are more efficient. So let's move on to next slide. So you can look here two programs, one is the original one and the other one is optimized one. In original one we are at 0 state, we are initializing, we are declaring two variables x and y, then there is a loop 1 which is always true, then we have while not go. So as long as this statement is true, it will not come down. When this statement gets false, because this is an infinite loop, the value of x underscore I will get assigned to x and y underscore I will assign to y while x is not equal to y. So here we have an example GCD of 42 and 8. So obviously 42 is not equal to 8. So the next condition that is going to be checked is if x is less than y. No, x here is 42 and y is 8. So we will get into else statement. So 42 minus 8 we will get 34. So now x will be 34 and there will be no change in y. So you can see that this is our output. Okay, so traversing till here 2 2, the GCD will be 2 and it requires almost 9 iterations to complete the loop, that is this loop, while x is not equal to y. Now if we replace this subtraction with modulo, the program will speed up. So this is our modulo function. Rather than having two subtraction, we can just use single modulo operation, that is your remainder operation. So likewise we are declaring the variables x, y and r remainder while for infinite loop always in taking input. While not go, it means that if go underscore I is not true, okay, so it will keep on looping here. When this statement becomes false, it will go down and check if x underscore I is greater than y underscore I. It means that if x is greater than y, so assignment will be x and y. So in our case x is 42 and y is 8, so this loop is this statement is fine, we will not come here. So while y is not equal to 0, so obviously y is not equal to 0 because y is 8. So x mod y, so if we divide 42, if we divide 42 divided by 8, the remainder will be 2. Okay, so now x is equal to y, so x will have the value that was in y, that means x will have the value 8 and y will have the remainder that is 2. So you can see here in this step we have 8 comma 2 and in next step we have 2 comma 0. So here we computed the GCD that is 2 and here we have computed the GCD that is 2. In 2 steps, here we need only 3 iterations, 1, 2 and 3. Here we need 9 iterations. So obviously this is very fast. However, do not go on to the states, like here you can see 9 states and here you see 13 states, but this is faster compared to this one. Okay, so this is how you can optimize your original program. Clear? Now let's move on to next slide. So in previous slide we were discussing about optimization of the program or the algorithm. Now we will talk about the optimization of the finite state machine with data. So there are 3 possible areas of improvement. Either we can merge states, we can separate state, or we can schedule states. So merging states mean where the states are constant on transition, we can remove those states. Where there is no change in these states during transition, we can eliminate those states. Transition taken is already known because transition taken is already known. States with independent operation can be merged. Those states which have independent operation, we can merge those states. We can separate states with complex operation. For example, A multiply B multiply by C can be broken into smaller states to reduce hardware size. Now coming towards the scheduling is this task of assigning operations from original program to states in an FSMD. So we assign operation from original program to states in the FSMD. The scheduling obtained using the template method can be improved. Consider the original FSMD for GCD. Okay, state 1 is clearly not necessary. So what we do, we check at the finite state machine diagram and we check at the program and we make sure that whether this state is necessary or not. We will look into this in next slide. So here on the left side we have original FSMD and here we have the optimized FSMD. You can see we have this one is independent assignment. Before that we have 2 separate assignments, so they are combined. This is known as what we call it scheduling. This is not necessary, so we can get rid of this. So I'm going to read this one by one. So eliminate state 1. Transition have constant values. So if you move from 1 to 2, there is no change. So we do not need 1. We can start from this 2. Okay, so we can start from this 2. So initialize x and y because there was no change in x and y up till state 2. So we can directly start from there. Merge 2 and 2j. No loop operation in between them. So if you see 2 and 2j, there is no operation. We are not performing anything between 2 and 2j. So we can simply merge them and we can use this. You can see this arrow. Okay. So we can simply this place, which were before this one state to another state. So merge 3 and 4. So assignment operation are independent on. So these are independent operation. This one is on x and this one is on y. So we can merge. So this is 3. Merge 5 and state 6. So transition from state 6 can be done in state 5. So we can merge 5 and 6 because what we're trying to do, we're comparing x not equal to y not. So once this is false, we can directly come to this. Rather than coming to here, we can directly come to 7 and 8. So this is 7 and this is 8. Okay. So eliminate 5j and 6j. Because we have eliminated 6, we do not need 5j and 6j. Transition from each state can be done from 7 and 8. So we can directly come from 7 to 8, 7 to 9 is, yes, we can directly come from 7 to here and from 8 to 9. As you can see here, transition from 7 can be done 7 to 5 and 8 to 5. So let me just clear this out. So previously we were going from 5 to 5j to 5j to 5, but now we can go from 7 to 5 directly. You can see here. Okay, 7 to 5 and 8 to 5. This is the arrow showing. Okay, so from where we can move. So the last one is eliminate 1j. Because we do not have this state now, this state, so we do not need 1j. We can directly move from 9 to 2. So this is 9 to 2. So here we have not optimized the code, rather what we have done, we have eliminated state 1 because transition have constant value, x and y was not changing. We merged 2 and 2j because there was no operation between them. We merged 3 and 4 because assignments were independent. We merged 5 and 6. Transition from state 6 can be done because we can transition from 6. What we were doing from 6 can be done from 5 as well. Okay. Now 5 and 6j was eliminated because we can directly move from 7 to 5 and from 8 to 5. Eliminating 1j, and we can traverse back from 9 to 2 directly. Okay, so now this is optimized. You can check that 1, 2, 3, 4, 5. Now we have only 5 states. Previously we have like almost 10 states. So that was about optimizing the FSMD. There are two things that I would like to point out here. Annotation is the task of choosing which register transfer component to use in datapath, whereas binding is the task of mapping operation from FSMD to allocated components. The last way of optimization of custom single purpose processor is optimizing the finite state machine. So there are two possible ways by which we can optimize the finite state machine. Number one is state encoding. In state encoding, we assign unique bit pattern to each state. Okay. For example, we have a state A, state B, state C, and state D. We can encode these state as 00 for A, 01 for B, and 10 for C, and 11 for D. Now, size of state register and combinational logic vary. It is not necessarily the size of these two are equal. Can be treated as an ordering problem, so we need to have proper sequence for state encoding. State minimization is a task of merging equivalent states into a single state. How we can merge them? State equivalent if for all possible inputs combination the two state generate. If two state generate same output, okay, and transition to next state, then we can merge them. Okay, if there are two states and these two states are generating the same outputs in the next transition, so we can merge them. So that was about it. The state merging that we did when optimizing our FSMD was not the same as state minimization as defined here. Okay, the reason is that our state merging in FSMD actually changed the output behavior, in particular the output timing of FSMD. Typically, by the time we arrive at in FSM, we assume output timing cannot be changed. State minimization does not change the output behavior in any way. Okay, so changing timing is different compared to state minimization. State minimization does not change the behavior in any way. So that was about the state minimization and optimization of SSM. So in summary, we have seen that in order to design a custom single processor, we have straightforward techniques. You need to understand what is truth table, you need to understand what is Boolean extraction, you need to understand the input and outputs of combinational logic, you need to understand the sequential logic, you need to understand the state tables, and then you need to understand how you can convert the complex finite state machine with data to finite state machine and data path. What are the steps for designing the data path? How you can optimize the data path and finite state machine. So we can use custom single purpose processor to execute small algorithm. Typically we start with finite state machine with data, as I have shown you in the example of bridging. CAD tools can be used and it can provide great assistance in aiding the designer. Okay, so that was all about designing the single custom processor. Thank you very much.